Hello all and welcome to this video where we look at exponential growth and decay. So this is our applications of exponential equations. They're all based around some function of x is equal to a to the x. It's based around that idea. It's just a modification of that, changing the base, changing the exponent in some way, maybe applying some factor out the front when we think of percentage growth or interests and compounding, things like that. So it's all based around that exponential equation. It's just modifying it to different situations as needed. For cell growth, that is where we have, I guess you could think of it, we have a base 2 because for cells, we have an integer amount of cells. We can't have 1 and we can't have 1.5 cells. We have 1, it divides, we have 2. Those divide, we have 4. So that's why that exponential base 2 comes into it, if you think of that. Little t is our time duration, and then capital T is the generation time. So how long it takes for a split to occur. N naught is the number of cells initially. So subscript naught is your initial situation, and then n is the number of cells final. Radioactive decay is very similar. This time we have base E because, as we talked about in class, we get that base E when something's growth or decay is directly proportional to how much there is. The rate of change of f of x is equal to e to t. We remember very briefly, okay, the rate of change of that is also equal to e to t. So it's directly proportional to how much there is, and that's the thing with radioactive decay. The more of it, the more it decays. The less of it, the less is decaying at any one time or over a time period. The thing to note is this k, that's a positive constant that is then made negative as part of it, going with the assumption that the material is decaying, it's having radioactive breakdown. That's dependent on the type of materials. Uranium will have a number, plutonium will have a number, they all have different numbers. A naught again is our initial amount, and then we are left with some final amount. Population growth, this percentage one and decline is very similar. It's actually almost identical to compounding interest that you would have seen before. It's that same idea. It's a percentage rate, increase or decrease. We're starting with some initial amount, and we consider these two equations the same equation. You can consider a plus or minus, and we're just changing that in case the population is increasing, or it's a negative if the population is decreasing. Again, we're starting with some initial population amount, and then the change is occurring to. Now, here's where a lot of people get caught out. We have some rate, which needs to be a percentage, and that has an applied, because it's a rate, it's a per time, okay? So it could be 5% per year, it could be 5% per 10 years, it could be 5% per month, it could be 10% per month, something maybe to do with rabbits. Now, N needs to be the matching rate, okay? Matching the per time period. So you might be given a rate in a very common problem might be what's the population growth over 36 months when the rate is growing at 5% per annum. Okay? Per annum means per year. That means you actually need to convert the time period, the number of days, the months or years, you need to convert it to the same as your rate. So in this case, the 36 months, we need to actually convert that to years, so that's the same as 3 years. So our N would have to be 3 in that case, not 36. So that's the really common way where they try to catch you out with that problem, is converting the time period to match the rate. So that's our equation, so let's get straight into using them. A population of 2,000 pathogen cells doubles every 15 minutes. Determine the formula for the number of pathogens at time t minutes. Well, this is a cell growth one. So we have n is equal to n naught. It'll be base 2 to the t on td. Okay. So we will get, in this case, n of t. It's asking for a formula, so you could consider that just an equation. It doesn't need to actually be a function. We get is equal to 2000, because that's the initial amount we have, times by 2 to the t on, and we put divide by 15 because that's the doubling time. So that's our TD, and the little t is how much time has actually elapsed. How long will the population take to reach 12,000? Give your answer correct to the nearest minute. So we're going to let n equal to 12,000, and that means we get 12,000 is equal to 2,000 times by 2 to the t on 15. Now divide both sides by 2,000. We're going to get 6 is equal to 2 to the t on 15. Now we need to get the t by itself, so this is where our logs come in. So we can take log of base 2 of both sides. So we could go log 2 of 6 is equal to log 2 of 2 to the t to the 15. Now, since this t to the 15 is a power, we can bring that out the front just like one of our log laws. So we get one color. Log base 2 6 is equal to t on 15. Log base 2 of 2. Log of base 2 of 2 just turns into 1. So we can just go with that. Let's come up here and take the 15 over. So we get 15 log of base 2 of 6 is equal to little t. So little t is equal to, put that in the calculators. My bag here. Okay. Yeah. Oh, that's log base 10. I don't want log base 10. I just pulled out my scientific. CAS. Let's bring out my CAS software. I apologise for the delay. Okay, here we go, main, and I want keyboard. And what did I want? I want 15 of log base 2 of 6. Incorrect number of parameters. Oh, I still got this random solve stuff up here, do I? Let's go edit, clear all. Let's try that again. 15 times by log base 2 of 6 equal to 38.77. Okay. Time is equal to 38.77 minutes. Okay. And correct to the nearest minute how long it will take to population reach 12,000. So time is going to equal to 39 minutes. Now here's a little interesting one where we need to be thinking logically, is that we're not always going to be rounding up or down to the usual. If it's above 0.5, round up. If it's below 0.5, round down. What would have happened if we had have got 38.27 minutes? Well, we can't round down to 38 because at 38 the population wouldn't have reached 12,000. Okay, it took until 38.27 minutes. So to properly answer this, it's asking to reach 12,000. So we can't say a time before that because it's reached it at technically 38.27, or an actual answer was 38.77. But even if it said 38.27, you would have to round up. Okay, because you can't say 38 because it hasn't actually gotten there yet. 39 would be the closest correct answer. Rightio, after 3,000 years, a sample of magnesium-23 has decayed to 40% of its original mass. Determine the formula for radioactive decay of magnesium-23, where K is a positive constant and T is time in years. Well, this is a decay one, so we have, and we used A and A naught. A is equal to A naught E to the negative KT. Okay. So we could have that one, and then determining, we'd follow on. So it's decayed to 40% of its original mass. So we could just say it started with a kilo. We could say it started with 100 kilos, 1,000 kilos. It doesn't matter what we say we started with. We're at 40% of its original. So I'm just going to say that A0 equals 1, and then the final amount is going to be 40% of that. So that's just going to be 0.4. That's going to make our life a little bit easier. E to the negative kt, and our time was 3,000 years. So we got 3,000. So yeah, we get that's our formula. Now find the value of K, correct 7 decimal places, and hence find the half-life of magnesium-23. So let's look at the first bit. We need to find K. So we had our formula, which is 0.4 is equal to the one we don't need to write. We just get e to the negative K, 3,000. Take log base e of both sides. Let's actually write it as log base e. It's not log. 0.4 is equal to negative K by 3,000. So we're going to get, if we divide both sides by negative 3,000, we get log base e of 0.4 divided by negative 3,000. And this is a time where people really, because they're trying to fit in a fraction, they don't put the e as a subscript. People will write that because they're trying to fit it in. That's wrong. You need to write that e as a subscript. And that's going to be equal to K, so we can put that in our calculator. And we're going to get fraction. We want, we don't need to use that one, we can just use fraction. We can use ln, log natural means log base e of 0.4 divided by negative 3,000 is 3.05430. Okay, so let's write all that out. K is equal to 3.0543024. That was 1, 2, 3, 4, 5, 6, 7 decimal places. And then the calculator says E negative 4. E negative 4. So what's that mean? That's a capital E negative 4. That's actually saying times by 10 to the negative 4. Scientific notation. That's the K value. That's just what it is. It's a parameter. So we get that. So we found K, and now it's asking hence find the half-life of magnesium-23. The half-life is for any materials how long it takes for it to decay to where it only has 50% of its original mass. So in this case, same thing, we can let A equal to 0.5 because we want 50% and our original amount is just 1. So similar sort of situation, we are now getting 0.5 is equal to 1e, and now we have K, so we can put that in, negative 3.0543024 by 10 to the negative 4 by t, and that's what we're trying to figure out t. So same thing, we can take the log natural of both sides. So we get log base e of 0.5 is equal to negative 3.0543024 by 10 to the negative 4 t. That means t is going to be equal to log base e of 0.5 divided by negative 3.0543024 by 10 to the negative 4. Cannot forget that, by 10 to the negative 4. And let's stick that in our calculator. Fraction of natural of 0.5 divided by, I'm just going to stick it in brackets because it's my habit just to avoid, actually no, I'm not going to need to because it's got the fraction, lovely fraction operator on this version of the CAS. So we get negative 3.0543024, and we want that. Is there an automatic by 10? Doesn't scream out there's a on scientific calculators they have a times by 10 to the power of something button, but it doesn't shout it here, so we're just going to go times by, use, not that one, need to put the 10 in first, it seems. Put 10 in. We're going to use this button just below the line button, times 10 to the negative 4, hit enter, and we get 2,269 years. 2269.41. 2269.41. So the time of the half-life is roughly equal to 2,200. And you could say 69 again. You could probably round up to 2,270 because you need to elapse the whole 50%. So it's roughly 2,270 years, which makes sense. If it takes 3,000 to decay to 40%, you need to be getting close to that amount to decay half of it, so 2,270. That's that example. How are we going for time? 16 minutes. So let's get through this example quickly. In a large country town, population of P0 of rabbits started 2003 was 3,500. By the end of 2013, this number increased to 27,000. Assume exponential growth. Determine the formula for this population growth of rabbits, where R is the rate as a percentage and N is the number of years since the start of 2003. So we get P is equal to P0, and our formula there, that's population growth, P0, 1 plus R on 100. 1 plus R on 100 to N. And in our situation, we actually have 27,000 is equal to 3,500 on 1 plus R on 100, all to the power of, and the number of years, 2003 up to the end of 2013. So start 2003, so end of 2003 is 1 year, and then we go from there. We have to add another 10 years. So actually in this case, it's got to be read carefully. It's the start of 2003 to the end of 2013, and is actually 11 years, so we get 11 there. That's what we get to use, hence find the value of R to find the predicted population of the... No, got to read the question properly. Find the value of R, so find our rate, and then hence find the predicted population of the rabbits at the end of 2020. So we're going to solve equation. Get 1 plus R on 100. The 11 divide by 3,500 both sides. We get 2700 divide by is equal to 100 to 11. So let's take log base 11 of both sides. Wait, no, we don't want to take log base 11 of both sides. We need to take the 11th root, that's right, because we're not actually trying to figure out the exponent. We're actually trying to find R, which is inside the exponent. So we actually need to take the 11th root of both sides, because that would be like, you can imagine that being a square there. How do we get rid of the square? Well, we take the square root. If it was a cube, we take the cube root. So this time we're going to take the 11th root. 3,500 is equal to 1 plus R on 100. Subtract the 1. minus 1. Multiply that all by 100, and that's going to give me my rate. So R is equal to, get the calculator up again, 100 times by the 11th root, put a fraction inside there, 27,000 divided by 3,500, take away 1, close brackets. That gives me a rate of 20.41. We'll go with that, 20.41%, and that was a per annum because we worked that with years. Now we need to find the population when t is equal to, now we started at 2003, we're going to the end of 2020, so you've got the 1 year to get you to the end of 2003, and then another 17 to get you to the end of 2020, so that's actually going to be, now n is equal to 18. So population when n is equal to 18 is going to be equal to 3,500 by 1 plus, our rate was 20.41 divided by 100 to the 18 is equal to bracket 1 plus fraction 20.41 divided by 100, close bracket, all to the power of 18. I'll put a times symbol in this because the 3,500 is technically not to the power of 18. So we don't want to make the CAS confused. Gives me 99,081.83. 99,081.8. 0.81.8. Again, this is a time where we need to think logically about, should we round up or down? Can we have 0.8 of a rabbit? And technically, have we gotten that full rabbit by the end of 18 years? The technical answer is no. So it'd be 99,081. And that's your answer, and that's the end of the video. 2 minutes over time, but I hope that helps. If you have any questions, please let me know in the comments before, or in Google Classroom, or shoot me an email. Thanks and have a good day.